in the previous lecture we discussed the quantitative model of the energy versus wave vector relation, the EK relation for electrons in a periodic potential. So we outlined 3 important features of this EK relation based on the solution of the Schrodinger's equation. The 3 features were: 1, that the EK relation is periodic with a periodicity equal to 2 pi by the interatomic distance. So we considered a one dimensional situation where you have all the atoms located along a line in a regular fashion. The next feature was that certain energies are present for which the Schrodinger's equation has no solution for real values of the wave vector k. And the third feature was that for any given value of k there are multiple values of the energy E allowed for electrons in a periodic potential. In contrast to this EK behavior, the EK behavior of a free electron is very simple. It is a parabola in which for any given k there is only one E, or if you consider the EK relation for electrons in a rectangular potential well, then the EK relation consists of a set of discrete points on a parabola. For any given k there is only one value of E. So although we did not discuss the solution of the Schrodinger's equation for a periodic potential in detail, we outlined the important steps and showed how from these important steps the 3 features, namely periodicity of the EK relation, E being a multivalued function of k, and the absence of the solution of the Schrodinger's equation for certain energies for real k, or the presence of forbidden energy bands. These 3 features, how they emerged from the solution, this fact was outlined. Then we said that since the EK relation is periodic, it is not necessary to show multiple periods of this relation. We can show only one period, and that will consist of all the required information. Now this one period is called the first Brillouin zone. Now in fact, since the EK relation is even, one need not even show the EK relation for one period, one could show it for even half a period or half of the Brillouin zone. Now it is in this form that the EK relations of real crystals, for example silicon and gallium arsenide, are shown. So we showed the EK diagram of silicon and gallium arsenide, and we just presented the important features of this EK diagram. Now in the lecture today we would like to discuss the utility of the EK relation, and we would like to move on to the EX diagram and discuss how we can determine quantitatively the EX diagram. Let us begin with the utility of the EK relation. This relation helps us determine the velocity, momentum and mass of a carrier in a crystal having a given energy E. Now you might wonder that isn't this determination very simple, that is the determination of the mass, energy and momentum of a carrier of a given energy. Now so far we are used to a free electron, right, calculating various quantities for a free electron. Now for a free electron the mass does not change with energy, the mass is a constant. For a free electron the energy momentum relation is simply energy is equal to p square by 2 m naught, and therefore if I want to know the momentum for a given energy I can simply use the formula P equal to square root of 2 m naught E. If I want to know the velocity of the electron for a given energy E, assuming the energy to be kinetic energy, because that is when you can write E as P square by 2 m naught, you can get the velocity as follows. So E is equal to half of m naught v square, and therefore the velocity v is nothing but 2E by m naught under square root. Now all this is fine for a free electron. But for electrons in a crystal, things are not so simple. We will find that the effective mass or the mass of the electron depends on energy. Similarly, the energy versus momentum relation is more complex, right? So let us look at these features. Let us start with the carrier velocity. Okay. Now the carrier velocity of a carrier, which can mean an electron or a hole. So whenever I use the term electron, you must always remember that you can also use the same idea for a hole. So for an electron in a crystal, the velocity is the group velocity. Why? The electron wave has to be in the form of a wave packet in order to be localizable. So we have pointed out that when you want to discuss the behavior of electrons in a crystal, in contrast to the situation for a free electron, the electrons in a crystal have to be treated quantum mechanically, or the electron should be regarded as a wave. Now once you regard the electron as a wave, it has to be in the form of a wave packet in order to be localizable, and therefore the electron velocity is equal to the group velocity of the wave packet, which is given by the formula Vg equal to 1 by h cross into the gradient of the energy E, where the gradient is obtained with respect to the wave vector k. Okay, that is what this formula means. So this is where you have to use the Ek relation. So the slope of the Ek relation actually gives you the group velocity. Let us look at the carrier momentum. The momentum of a carrier is given the name crystal momentum. Now let us see what is the origin of this name, how the particular momentum of a carrier that we employ in a crystal is different from the true instantaneous momentum. A carrier does have a true instantaneous momentum in a crystal. However, as we will see, it is not possible to determine this true instantaneous momentum easily, and instead we use a momentum like term that we call as crystal momentum. So an electron subjected to a force F for a time dt experiences an increase in electron energy of dE equal to the force multiplied by the velocity. This is a dot product, because force and the velocity, which is the group velocity, are both vectors, and so you have to take a dot product multiplied by dt. So force into velocity is power, and when you multiply power by time, you get the energy. Now you can write this formula as f of dt by h cross dot product of this with the gradient of the energy with respect to k, because just now we discussed the fact that the Vg is equal to 1 by h cross time gradient of k. Now we know that we could write dE as gradient of E with respect to k dot dk. Okay. Now this is from elementary calculus. dE is equal to dou E by dou K into dk. Now when you take in 3 dimensions, this is written as I into dou E by dou kx plus j into dou E by dou ky plus k into dou E by dou kz. Now it is important to note this k and this k are not the same. This is the vector in the z direction, unit vector in the z direction. Okay. So this multiplied by I dkx plus j dky plus k dkz. Again this k with a hat is a unit vector different from the wave vector k. Okay. So this is how you get dE from elementary calculus. Now that is what is written here. Now you can even write the same thing as dk dot the gradient of E with respect to k. Now from this relation and the relation for dE given here, we get f of d f into multiplied by dt divided by h cross is equal to dk. Now this is because you compare this and this relation. So you remove the gradient of E with respect to k from here and from here, and you get this term is equal to this term. That is what is being written here. Now the same thing can be written as f is equal to d by dt of h cross k. Now look at this relation, f equal to d by dt of h cross k. This relation tells you that h cross k can be regarded as some sort of momentum which is conserved in the interaction of electrons with a force or other entities. Now this is like a Newton's second law, right, relation between force and momentum, which you are familiar with, and this second law also implies conservation of momentum in the absence of a force. Now the h cross k term is not equal to the mass of the electron wave into the velocity of the electron wave, which is the group velocity, and therefore h cross k is not to be regarded as the true instantaneous momentum. Now this is an important point. Although the equation f is equal to d by dt of h cross k points towards calling h cross k as some sort of momentum, it is not the true instantaneous momentum, which is given by the mass into velocity. As we will shortly see, the mass of the electron is not constant with energy, and you have to use some sort of an effective mass. Why? Because of the presence of the periodic crystal potential or crystal forces from the atoms. Therefore we give a different name to h cross k, we call it as the crystal momentum. Now let us distinguish between true instantaneous momentum and crystal momentum to understand the concept of crystal momentum much more clearly. For an electron of energy E subjected to a crystal potential UC of x, the difference between the true instantaneous momentum and crystal momentum equal to h cross k is as follows. The true instantaneous momentum is not a constant of motion, whereas the crystal momentum h cross k is a constant of motion. Now let us illustrate this point with an analogy of the car on a wavy road. Now supposing I have a wavy road like this, and there is a car moving on this. Okay, let us assume that when the car is at the peak here, it has a velocity or speed v. Let us further assume that there is no friction between the car and the road and the gravity is acting, and therefore when the car moves down, its velocity is going to increase in magnitude and of course changes in direction also. Now by the time the car is here, its velocity will be maximum, it will be very different from this. So you can see here, when the car is moving on this wavy road, if I were to look at its true instantaneous momentum, that momentum will also be fluctuating. So if I plot as a function of time for this car, so there is a certain momentum, then it reaches a maximum, so there is certain momentum here, it reaches a maximum, and then again it goes minimum and so on. So you can see that if I talk about the true instantaneous momentum of this car, when the gravity is acting on it, because of the action of the gravity and the wavy road, the true instantaneous momentum is not a constant. Now a picture for the electron in a crystal is similar. The electron is subjected to a periodic crystal potential, and therefore you cannot deal with the true instantaneous momentum because it is going to be affected by the crystal potentials. Another difference between the two is that the true instantaneous momentum cannot be calculated from quantum mechanics easily, whereas the crystal momentum can be easily calculated from quantum mechanics. Let us move on to the concept of carrier mass. The carrier mass in a crystal is referred to as effective mass because you try to incorporate the effect of crystal potential on the carrier acceleration due to a force in the mass. So when you apply a force, the carrier will accelerate to a different extent in a crystal as compared to a carrier in vacuum. Okay? Now we have discussed the concept of effective mass already. Now we will discuss how it can be calculated. So the basic point is that for an electron in a crystal, if the force is acting in some direction, the acceleration is not in the same direction because of the presence of crystal potential. So the effective mass is actually a tensor. Now this matrix representation you have come across already in the second module or the module on the qualitative discussion of carrier transport, which is repeated here. So what this matrix says is that the x-directed acceleration can be due to fx, fy and fz, and each of these components will have a mass associated with it. So that is how you have 3 masses, okay, which contribute to every direction of acceleration, and therefore you have 9 different terms here associated with the effective mass. Now let us see how we calculate these terms. So in a compact form we can write m suffix ij inverse is equal to ai by fj, where I refers to the directions x, y and z, and similarly j also refers to directions x, y and z. So for example, if I take this term mxx, that means I and j are x, and this is given by ax by fx, this is ax and this is fx. On the other hand, if you take this term mxy inverse, so I is x, j is y, and so this is equal to ax by fj. Now let us write the acceleration and force. So the acceleration is given by the gradient of the velocity with respect to time. So this is d by dt of the group velocity in the I direction. On the other hand, the force Fj is the time derivative of the crystal momentum h cross k in the j direction. Now Vgi can be written as dou E by dou H cross Ki, where H cross Ki is crystal momentum in the I direction. We have already defined the group velocity and shown how it is equal to dou E by dou of H cross K. Therefore, d by dt of Vgi is nothing but dou by dou of H cross Kj applied to this particular group velocity term multiplied by the time derivative of H cross Kj, right. This is from elementary calculus. So you take this term and you want to get its derivative with respect to time, you take the partial derivative with respect to a particular term, and then the time derivative of that term is what is multiplied here. Now therefore, if you substitute this term here, it works out to Mij inverse is equal to dou square E by dou of H cross Ki into dou of H cross Kj. Now this is how you calculate the particular term of this effective mass tensor. Okay. Now this is how the Ek relation can be used to determine the effective mass. So in general the Ek relation will be fairly complex when you look at the 3-dimensional picture. Now let us illustrate these ideas using a 1-dimensional situation. So for a 1-dimensional case, let us say this is the Ek relation as shown here in the first Brillouin zone. These are the points where the slope of this Ek relation is maximum. Now the group velocity is the slope of this Ek relation, and that works out to something like this. Now this is interesting. Now what does it mean? So you find that the group velocity increases linearly with k, and k represents in some form the crystal momentum, because H cross k is crystal momentum. So k is proportional to crystal momentum. So the velocity is increasing linearly with momentum. This is somewhat like the picture of an electron in vacuum. However, as the energy goes on increasing, you find that at this point the velocity has reached a peak, and thereafter even though the momentum is increasing, the velocity is decreasing. Now this appears counterintuitive, right. This is not something that you would expect. Now this is something that we have to accept from the analysis of electron in a crystal based on quantum mechanics. Okay. Now what you find is, even as k is increasing beyond this point, the velocity is going on decreasing and it goes to 0, and if you try to increase k further, in fact the velocity goes negative. Now that negative part can be constructed from here, this part, because the negative part here beyond this pi by a point, k equal to pi by a, is the same as the negative part here because of the periodicity. So the velocity is going negative as you increase k, and then it reaches a maximum negative velocity, and thereafter the velocity starts decreasing in magnitude and ultimately goes to 0 for value of k, which is 2 pi by a, which is same as k equal to 0. So k equal to 2 pi by a, which comes somewhere here, is the same as k equal to 0 because of the periodicity. Now what does this mean? This means that if you try to accelerate an electron in a crystal by applying a force, it is not as though the electron will move in the direction of the force all the time. We think from our experience, daily experience with free particles, with free electrons and so on, that when you apply a force, the momentum of the carrier goes on increasing continuously, right. If the force is constant, the momentum increases linearly, the velocity increases linearly. Whereas what we find here in the crystal from this diagram is that the velocity increases up to a point, and beyond a point it starts decreasing. Now this means in a crystal if you apply a force to an electron, it will exhibit an oscillatory motion, right? So it will move, and then at some point it will change its direction and then come back because velocity becomes negative, and then at some point here, so the electron is moving against the force. How can this happen? It is the effect of crystal potential and the wave nature of electron, and at some point here the electron changes its direction again and it keeps moving to the right. So in response to a constant force with time, an electron in a crystal will exhibit oscillatory motion. In practice, however, we are not able to see such an oscillatory motion. Why? Because even before the electron energies increase to a point where this behavior sets in, where the velocity reaches a peak and comes down, the electron will get scattered because of the presence of impurities and random fluctuations in the crystal structure, which will always be present in practice. So because of defects in the crystal which are always present, you never observe this oscillatory motion. So electron will get scattered, and therefore in practice the energies of the electrons would be somewhere in this region. You will never go to this region, right? You can't increase the electronic energy to that region, to that magnitude. Okay, now what does this mean for the mass? Now the mass is given by the double derivative of E with respect to k, of course with a inverse sign here. So I differentiate the velocity and then I take its inverse, and then I get this picture. So you can see here that the region where the velocity increases linearly with k is like the picture of electron, a free electron in vacuum. The mass of the electron is constant, though it is not equal to the mass in vacuum, but still it is a constant. It is some effective mass whose value has to be obtained from the slope here. However, as you reach this point here or here where the EK diagram slope reaches a maximum, the effective mass approaches infinity, okay, because the velocity is peak. If you take the slope of this velocity, it will be 0 and 1 by 0, because there is an inverse operation here, reciprocal. So 1 by 0 goes to infinity, and when you move to the other side here, when the velocity is decreasing with momentum, your effective mass is negative, okay, and it starts from a very high negative value, infinite negative value, and then goes on decreasing and reaches some value depending on the slope of this graph. Now the same kind of a segment appears on this side, okay, which is related to the velocity behavior shown here. Now let us just explain in a few lines what is the reason that effective mass is changing. Well, this is related to the fact of the change in velocity. You are applying a force, and at some point the velocity, beyond some point the velocity is not increasing. What does it mean? The mass has become infinite. If the mass is very large, a force cannot give rise to any acceleration, and so therefore it does not change the velocity. Now that is what is happening here. So the velocity reaching a peak and not changing in this small region amounts to infinite effective mass. So the velocity increasing at a decreasing rate here in this region is because the effective mass is going on increasing. So your force is constant, the mass is going on increasing, so the amount of increase in velocity is going on decreasing. So that is how it is, and very interestingly the effective mass is negative for electrons near the top of the band. In fact, it is this behavior near the top of the allowed band for electrons which involves a velocity against the direction of the force and a negative mass. It is this feature which is responsible for treating electrons close to the top of a band as positively charged carriers or holes. That is why electrons in the top of the allowed band, in the valence band, so this is the valence band, and this is the conduction band, right. So while electrons near the bottom of the conduction band can be treated as equivalent to free carriers but with a different mass, the electrons at the top of the valence band will be treated in terms of a positively charged carrier, right, because the electrons are moving in the direction opposite to that of the force, and this is the origin of the concept of holes. You want to know more about it, you can read our books. Here we would like to move on to other aspects of band diagram which are used in practice to analyze devices. Now let us look at the probability distributions of the electrons throughout the lattice and relationship of this distribution with energy bands. So here we are plotting the wave function psi magnitude squared. Okay. Now this wave function is solved for from the Schrodinger's equation. In the previous lecture we have shown some example of a psi x that has been solved from a somewhat realistic crystal potential, right. Now these are the kind of calculations which are represented here, except that here we are plotting the square of the wave function because we want to talk about the probability. Now if you take an energy level corresponding to a band from inner orbit, that is, this is the crystal potential, and if you take an electron very close to the atomic core, this energy level corresponds to that kind of a situation. Now for this energy level, the associated wave function gives rise to this kind of a probability distribution, where what you find is the distribution is reaching a peak at the location of the atom and it rapidly decays to 0. So what is the meaning of this? This means the electron can be found either over here or over here or over here and so on. This means that the electron is really bound to the atom, localized. On the other hand, if you take the wave function corresponding to a high energy, such as the one in a band which is corresponding to an electron far away from the atom, then you find that square of the wave function exists all over the space, albeit with different amplitudes. So even here there is a greater chance of the electron coming near the atom. However, there is a very good chance of the electron being found elsewhere too, and therefore the implication of this is that your electron can be moving about in the crystal. Now that is why electrons in the conduction band are assumed to be freely moving about in the crystal, whereas electrons in the valence band or in other lower bands are assumed to be localized to one of the atoms in the crystal. We shall now move on to the quantitative model of the EX diagram, that is the allowed energy levels as a function of distance. Now let us show how the EX diagram arises from the EK diagram. So let us put the two together because these two diagrams complement each other. Now for example, this is an EK diagram of silicon that we had shown in the previous lecture. Now if we consider an isolated uniform semiconductor, word isolated means that the semiconductor is not subjected to any electric field, okay, or any fields, and conditions in the semiconductor are uniform. That is what is meant by uniform semiconductor. Doping is uniform, composition uniform, temperature uniform and so on. Now in such a case we can draw the allowed energies for electrons as a function of distance as shown in this diagram, okay. So here the minimum point of the EK diagram is the energy level corresponding to this is represented as EC. This is the conduction band, and the maximum energy of the lower band, that is the valence band, is indicated as EV, and these two levels are constant with x because the semiconductor is uniform, right, and there are no applied electric fields. Now the top of the conduction band actually emerges from this point on the EK diagram. You also show the vacuum level E0 in the EX diagram. Even this level is constant. So what it means is the allowed energy level picture for electrons in an isolated uniform semiconductor is constant with X. That is what is represented here. Now we know that in practice the semiconductor will have some non-uniformity. It can have p and n regions, it can have junctions, the composition may change. One part of the semiconductor may be silicon, the other part may be gallium arsenide, and so on, and then you will apply electric field in order for the device, in order to make the device work, and therefore situation is going to be something like this. So let us say this is a semiconductor which is uniform in all respects except that an electric field is applied. Now in this case the bands bend as shown here. So the lines E0, EC and EV now are no more constant with X. So the semiconductor at this end is more positive compared to this end because electric field is from right to left. So at the right end your electronic energies are lower because this diagram shows increasing electronic energies as you move upwards. So as a function of X your electronic energies are decreasing, right, from left to right in correspondence to the direction of the electric field. Now how do you find out the slope of the lines and so on is what we are going to discuss. Now also I would like to mention here that we have not shown all the levels that are used in an energy band diagram to analyze devices. For example, the diagram shown here does not indicate Fermi level, which is a very important energy level used in the analysis. Now those are the levels which we are going to add onto this diagram, and we are going to discuss how can we calculate the various features of this energy versus X diagram. Now let us see the correspondence between this EX diagram and the EK diagram here. So the EK diagram shown here corresponds to the energy level picture at any particular X. When you apply an electric field, for every X the EK picture will be similar to this, however the values of the energies will change with distance. Now let us place the EX diagram in the context of the crystal potential to improve our understanding of the various bands and various energy levels. Okay. Now this is a crystal potential, a very large number of atoms here. We will consider an idealized one dimensional situation, and this is the crystal surface where the potential goes up to the so called vacuum level, okay, when you come out of the semiconductor here. So the surface is here, and when you come out of the semiconductor very rapidly the potential rises to the vacuum level. When you go inside, because of the atoms the potentials are low and it is periodic, something like this. So these are the locations of the various atoms in our one dimensional idealized semiconductor, A being the interatomic distance. So you find that the atom is located somewhere in between the two peaks, in fact exactly in between the two peaks here. Now in this crystal potential picture, this is the vacuum level E0, and these are the allowed bands of energies. Now the orange bands are the allowed energy bands, and in between you have the energy gap here. Similarly, there is an energy gap here, there is an energy gap here too. This line here shows that the width of the band is very thin. Now this is true for electrons which are close to the atom, okay. So the lower bands will all be very thin in width because the electrons are tightly bound. Now the potential energy of the crystal has been changed to the energy of the electrons in this diagram, okay, in this axis here. Now this is a conduction band, there is a band gap, there is a valence band, and you again have a band gap. This is the band from inner orbit, and this is the periodic crystal potential. Normally we do not show all these details, so we remove the crystal potential. Further, we do not show bands other than the conduction band and valence band and the band gap. Even further, we do not show the bands, but we show only the levels which correspond to the bottom of the conduction band, that is EC, and top of the valence band, that is EV, and in addition the vacuum level E0. So this is really the picture that we work with normally, okay. However, the set of slides that we showed just now should clarify the meaning of these levels, because when you look at them in the context of the crystal potential, things become very clear. Let us discuss the meanings of the various energy levels. Now we have come across energy band picture in the first level course. So what we are now going to do is really a review, a quick review, so that we can quickly move on to discussing methods of finding out the energy as a function of x. How do you calculate, okay, the energy as a function of x, and how do you use the energy band diagram to get information about electron and hole concentrations, the carrier current densities, and electric field and potential. So that is what we really want to discuss. So quick review: plotting electronic energy versus distance in an isolated semiconductor. You show the levels EV, EC, E0, and in addition here I have added the Fermi level. Suffix S stands for semiconductor. Since the semiconductor is isolated and we assume that it is uniform too, therefore all these levels are just horizontal. The distance between EC and EV is called the energy gap, represented as E suffix G. The distance between E0 and EC is referred to as electron affinity, normally represented using the symbol chi. So chi is really the potential in dimensions, and therefore Q times chi is the electron affinity energy. The difference between E0 and EF is the work function. So phi suffix S, S stands for semiconductor. We use the symbol phi for work function. So phi S is potential and Q times phi S is the work function in terms of energy dimensions. Now compare this diagram of the semiconductor with that of an isolated metal. Now here you have the Fermi level alone shown because you have overlapping bands, right? So you do not have anything like a conduction band edge and valence band edge shown here. You only show the Fermi level. Now all the electrons, most of the electrons occupy levels below the Fermi level. Now here most of the electrons are in the valence band in a semiconductor. That is what the shaded region shows, shaded region here too. The difference between E0 and EF is the work function. The work function in metal is shown as phi suffix m. Q times phi suffix m is the energy. Let us look at the donor level in the semiconductor. It is located close to the conduction band edge. We are talking about those donors which change the resistivity, that is the shallow donors. You can have a donor level far away from the conduction band edge also, but we are talking about donors which modify the resistivity, therefore the donor level is close to the conduction band edge. Similarly, the acceptor level which changes resistivity is shown close to the valence band edge. Now this distance EC minus ED and EA minus EV, these distances or differences are referred to as ionization energies of the impurities, because when a donor gets ionized, it becomes positively charged, and the amount of energy required to ionize a donor is equal to this gap that is shown here. That is why this is ionization energy. Similarly, when an acceptor gets ionized, it accepts an electron from the valence band. The energy required for this process is this difference. That is why this is called ionization energy. This is a level associated with a trap, which can be an impurity or it could be a defect in the crystal. Many of the defects which affect the transient response of the semiconductor or lifetime, they are near the middle of the energy gap. That is why this trap level is shown near the middle of the energy gap. It does not mean that you have a single level. In practice, you may have multiple levels located in many places throughout the energy gap. Now, this is the intrinsic level, which is very close to the middle of the energy gap. The distance between the Fermi level and intrinsic level is normally represented by the symbol phi suffix f. F stands for Fermi energy. Phi f is potential and q phi f is energy. Now, what does the vacuum level indicate? The vacuum level is normally referred to as local vacuum level in the context of semiconductors. Local vacuum level, right? The word local is important, although normally this word is skipped. Why? Because it refers to an electron which is localized on the surface of the metal or semiconductor, right? So it is not an electron that is removed far away from the semiconductor. When you use a vacuum level in the context of an isolated atom, you refer to vacuum level as the energy level corresponding to an electron which is removed far away from the atom, okay? So taken to infinity. Whereas when you come to the context of semiconductors, you talk about vacuum level as the energy of an electron that is outside the volume of the metal or semiconductor but touching the surface. So localized on the surface. That is why you must use the word local. So energy of this electron is what is represented by E naught. We will shortly see why we use a localized vacuum level, right? It will reflect all the built-in potentials inside the semiconductor. This point we will see later. Now, if the same electron is inside the semiconductor volume, then it could be located or it can have energies any of these locations, such as the conduction band, the valence band, or in a metal it would lie somewhere here. The difference between the energy of the electron and EC is the kinetic energy of the electron. So EC is the potential energy of an electron, a conduction electron. An electron that freely moves about in the crystal, that is a conduction electron. So the energy of conduction electron minus the energy EC, which is the potential energy of conduction electron. This is the kinetic energy. As against this, if you have a hole in a semiconductor, you won't have a hole in a metal. In a semiconductor you have a hole, then the EV minus the energy of the hole is the kinetic energy, because EV is the potential energy of a hole. Now let us introduce the donor and acceptor levels and talk about a few other energies in semiconductor. Rather few other processes on the energy band picture to see what these energy levels reflect. If you want to show the generation process, then this is it. An electron jumping from the valence band to conduction band, leaving behind a hole. Creation of an electron hole pair, that is what is generation process. So the electron is anywhere in the valence band and it jumps to anywhere in the conduction band. Now the process that is most likely, however, is the one for which the energy is minimum. However, in general, for a generation process, the energy can be greater than energy gap also. The recombination is exactly its inverse, an electron jumping into a hole, an electron in the conduction band jumping into a hole in the valence band. Impurity ionization. An electron jumping from donor level to conduction band, or an electron jumping from valence band to acceptor level, right. So here a hole is created, please note a hole is created here, but there is no free electron because electron is localized near the acceptor impurity. So the ionization of an acceptor impurity creates a hole which is free to move about in the crystal, but the electron gets bound at the acceptor impurity site. On the other hand, the ionization of the donor impurity creates a free electron and leaves behind a positive charge. That is why the positive charge is shown here near a donor level. Now this positive charge is however not a hole because it is localized near the donor atom, and so it cannot move about. That is why it is not a hole, it is a positive charge. Similarly, the acceptor levels, the acceptor level corresponding to acceptor atoms is indicated as a negative sign because when an acceptor gets ionized, it has a negative sign. Now with that, we have come to the end of this lecture. Let us make a summary of the important points. Now in this lecture, we have first discussed the utility of the EK diagram and shown how the EK diagram can be used to estimate the effective mass, the velocity or the group velocity, and the momentum or the crystal momentum of a carrier of any given energy. This information is useful in analyzing the motion of electrons in a crystal. Electrons are holes in a crystal. It is also useful to discuss the interaction of electrons and holes with other entities like impurities, phonons, photons, and so on, where momentum conservation principles can be applied. Then we began a discussion of the EX diagram. Okay, we showed how the EX diagram and the EK diagram are complementary. The EX diagram tells you the variation of the allowed energies as a function of distance, whereas the EK diagram tells you at any given location in the semiconductor what is the relation between the energy of the carrier and its momentum. So both these diagrams are very important, and any of this diagram by itself does not give the complete information. Then we tried to understand the various levels that are used to represent an EX diagram. We saw what is the meaning of these levels and how some of the processes that are happening in a semiconductor, such as generation, recombination, impurity ionization, and so on, are represented on this energy band picture. In the next class, we shall discuss methods of estimating these EX diagram for various situations and various types of semiconductors and devices.